Hello, everyone. I know I promised this discussion a little bit earlier, but I want to spend some time talking about orbits. And you can't talk about orbits without talking about Johannes Kepler. Kepler is the uh, natural philosopher at the time who made the transition from astrology into astronomy. He was very gifted in mathematics, which at the time meant little more than geometry. Algebra had not been invented yet, or at least not received by the Europeans. And, of course, arithmetic. So Kepler was working with fairly primitive mathematics. And a strong belief that God would make a understandable universe, that it could make sense. So the model which would ultimately be the model that Kepler was led to, and that affected what Galileo did, and that affected, of course, what Newton did, is that you put the sun at the middle of of the orbiting bodies. Plato had taught us that these orbits had to be circular, and Kepler held on to that idea as well, except Kepler had worked with Tycho. Get the last spelling right. Tycho. There you go. Worked with Tycho Brahe, or just Tycho. Everyone refers to him as Tycho. We're on a first-name basis, us physicists and the long-dead white men of Europe. And the important part about the heliocentric universe was everybody, including Kepler, was working on this model that circles were perfect, God was perfect, so we had to have circular orbits. But what Tycho brought to the mix was data. He had recorded the movement of location of the planets in their orbits to remarkable accuracy for the time. And that data met Kepler over the issue of the orbit of Mars. So Kepler tried for a very long time to make a circular orbit for Mars. And what he wound up with was that there were these things that were called epicycles at the time. And what epicycles were was just they were unjustified, unwarranted. No evidence supported them, except if you could figure it out, you could make these little sun, and then the orbits would do loops, which is saying, wait, that's not circular. But the loops would allow for the observations to sort of work. But these loops required that the Earth be at the center. So I've got to put a different object at the center of all this, because these loops would also include the sun, the so-called so-called geocentric model. But what our story with the data leads to is the idea of ellipses. The only way Kepler could make the data that Tycho had collected for the orbital motion of Mars was to assume that the sun, being the physical representation of God, was at the center, and then our orbits, and this is going to be a gross exaggeration, would come in as ellipses. And this is Kepler's first law of motion. This was scientifically important because it signified that we could take steps away from what had to be perfection. So in Kepler's mind, the perfection remained the sun, and the rest of it was just pudding in God's design. Recognize that with Kepler was also being worked with, Galileo was working in this time period, this was the era of the birth of science. Okay. What we now understand is that large bodies do in fact go around in ellipses, but they do so with the center of mass of the system as the orbital center for both the planet and for the sun. So the sun orbited this center of mass as an ellipse as well. The difference for our planets, however, is so small that we don't often get into the details. The important part of the first law is planets are in ellipses. Again, Kepler was doing his best to work with models that were perfect. He wanted things that illustrated geometric perfection. And these were the Platonic solids. They are essentially D&D dice, as we now use them. And you get yourself a four-sided dice. Of course, the cube is in this mix. So this would have 4 sides, 6 sides. This is going to have 8 sides, and so forth. The next one up would be a 12-sider, and then 20 sides. Okay, so what Plato was trying to do was fit these geometric objects into his elliptical orbital scheme so that he could then that he could then have that perfection. It didn't work. But what he did discover is if you take an object that's going in orbit and you take your four-sider, what you will discover, I better finish the orbit. What you will discover is that the triangles that were used to draw the motion of the objects reaffirmed the idea that that the area that the planet moved, red. What he found is that this area within the triangles was the same in the same amount of time. So if you will, he found that the change in the area was proportional to the change in time. So the area that was swept through was consistent with the amount of time it took. This turned out to be his second law. And his third law was really mathematically brilliant because he kept taking these triangles and shapes and trying to make them fit. And his relationship then became that in these elliptical orbits, the time it took to go around one of these orbits depended upon the cubed root of the semi-major axis. So in an ellipse, this is your major, and by this amount here is your semi-major axis, and that is what is used here. Since there are a number of planet systems that are actually orbiting in nearly perfect circles, it becomes okay for us to use circular orbits as an example of how this all works. So this is Kepler's third law. And as I indicated, I just wanted to give a quick rundown as what they are, because they ultimately are still working today, because once Kepler had it all figured out in terms of ellipses, people like Newton and Hooke and other scientists grabbed hold of these ideas and was able to use the Newton's law of gravity to basically prove all of these ideas. So Kepler's laws of gravity, and yeah, we'll use them in the next video.